All right, everyone, let's get started. I need your full attention for this. We're here for a mandatory training module on biofilm detection. I know some of you have been flagging inconsistencies with our current method, and you're right to do so. Today, we're officially moving beyond qualitative guesswork. We're going to break down why our old test is failing us and how we're shifting to quantitative certainty. So listen up, this is about getting the data right every single time. Okay, so to really understand the problems with our test, you first have to understand the dye itself. And believe me, it has a weird history. Congo red wasn't invented for microbiology, not even close. It was created back in 1883 in a German textile factory to dye cotton. The name Congo red? Pure marketing. In the 1880s, everyone was talking about the Congo River, so the company Agfa just slapped that name on it, and boom, it sold. It wasn't until 40 years later that a doctor noticed it could also stain weird protein clumps in human tissue, things called amyloids. And then it took almost 70 more years before it finally made its way into our world, microbiology. This winding path is really the perfect setup for our cautionary tale. And that brings us to the test that's been a staple in labs for decades, the Congo red Agar, or CRA test. For a long time, it was the go-to, cheap and easy way to see if bacteria were producing slime. But, our understanding of biofilms has exploded since then. We know they're not just slime, they're complex, organized communities, so our methods have to keep up. Let's do a quick review of how this thing is supposed to work. Now, the key word on this slide, the one that causes all the trouble, is selective. The idea is simple enough. The dye molecule is long and straight, so it lines up nicely with certain long, straight molecules in the bacterial goo, the matrix. When that connection happens, the colony changes color. But here's the catch, and it's a big one. It doesn't bind to any biofilm. It's incredibly picky. And that pickiness is the root cause of almost every problem we have with this test. This right here shows you just how picky it is. For staph, it's looking for one specific thing, a polysaccharide called PIA. For E. coli, it's looking for something totally different, these protein fibers called curly. But then you get to a major player like Pseudomonas aeruginosa, an expert biofilm former. Its matrix is built out of PSL and PEL polysaccharides, and Congo red just doesn't care. It ignores them. And what about biofilms held together by extracellular DNA? The test is completely blind to those too. So if a bug builds its house with the wrong materials, the CRA test tells you there's no house at all. So this is what you're left with at the bench, a system that's based 100% on just looking at it. Is it black, dry, and crystalline? Okay, strong positive. But what's the real difference between a moderate dark red with a black spot and a negative that's just a bit dark? Where's that line exactly? The truth is, it's blurry. What you call moderate, the tech on the next shift might call negative. That's not science, it's a judgment call. And that subjectivity is a massive quality control failure. Okay, so let's see what happens when these problems, the pickiness and the subjectivity, start to pile up. This isn't just an academic exercise. We're talking about a cascade of failures that can lead to wrong answers for critical patient samples. Let's look at some of the worst offenders. This slide is everything. You need to understand this. Look at these two pathogens. With Enterococcus faecalis, the CR test is a false positive machine. It is perfect sensitivity. It'll never miss a true positive, but its specificity is a train wreck, down around 7%. That means it mislabels almost every non-producer as a biofilm producer. It's crying wolf. Now look at Acinetobacter biomauni. It's the complete opposite disaster. The sensitivity is shockingly low, sometimes as bad as 3%. It misses more than 9 out of 10 true biofilm producers. So the test can be wrong in two totally different but equally dangerous ways. And this quote sums up the danger perfectly. For an organism like Acinetobacter, if you get a pink colony, you feel relieved. But that result is essentially meaningless. A negative on this test does not, and I repeat, does not rule out a clinically important biofilm. We cannot make diagnostic decisions based on that kind of uncertainty. It's just not acceptable. And the list of quirks just keeps going. Proteus mirabilis? Oh yeah, it can make those nice black colonies, but the stuff it's making has nothing to do with what the test is designed to find. E. coli, to get that classic result people talk about, you can't even use a standard protocol. You need special media with no salt, and you have to incubate it at room temp. Even Candida can be screened, but again, whatever the dye is sticking to, it's not the same stuff we see in bacteria. There is no one-size-fits-all protocol, which makes it a nightmare for standardization. So, we've seen that it fails. Now for the most important part of this training, understanding why it's so broken on a technical level. This is the knowledge you need when you're at the bench, looking at a weird result and trying to figure out what's going on. The single biggest reason this test is flawed is the total lack of standardization. There's no official validated recipe. Is your lab making it with a BHI base or TSB? Is there sucrose in it or glucose? You'll get different results. Did you incubate it at 37 or 35 degrees for 24 hours or 48? Again, different results. We can't have a reliable diagnostic test when the answer depends on which recipe someone downloaded from the internet. And here it is, the hidden trap. This explains so many of the false positives. We pack the agar with sugar to encourage biofilm, right? But what else do bugs do with sugar? They ferment it, producing acid. Well, it just so happens that Congo red is also a pH indicator. If the pH drops too low, the dye changes color all on its own. So a colony can turn dark simply because it's sitting in a puddle of acid, not because it made a biofilm matrix. The test has no way to tell the difference.
Okay, so enough about the problem. Let's talk about the solution. Effective immediately, we are moving to the validated gold standard for biofilm quantification, the microtiter plate or MTP assay. This is how we will be doing things from now on.
Just look at the difference. It's night and day. We are replacing subjective guesswork with objective measurement. We're going from looking at colors to reading a number. We're moving from a test that's narrowly specific to one that detects the total amount of biofilm, no matter what it's made of. Posel, PEL, eDNA, all of it. We are trading a flaky, error-prone method for one that is reproducible, reliable, and standardized. This is what certainty looks like. It's not sort of darkish red. It's not black, but not very crystalline. It's a number, an optical density value spat out by a machine. This value, 0.618, is a direct measurement of the biofilm biomass. There's no room for argument. There's no interpretation. It's just data. And here's the best part. That number isn't just for us in the lab. It translates directly into a clinical risk score for the patient. We can set clear, validated cutoffs. A reading below 0.120 means low risk. Over 0.240, that's a high-risk isolate. This gives clinicians actionable information to guide treatment. A CRA plate could never, ever do that.
So let's wrap this up by outlining the new protocol. This is the new standard of practice for this lab. Pay close attention because this is what you'll be expected to follow. Now, for anyone thinking this new assay sounds like more work, you'd be wrong. A 96-well plate might look intimidating, but when you factor in everything, media prep, streaking, incubation, and then standing around debating the color of a colony, the total hands-on time for the MTP assay is actually less. It's not just more accurate, it's more efficient.
Now let me be crystal clear. The CRA test is being phased out for diagnostic work. If you see it used for a research project, fine. But from a quality control perspective, there is a new mandate. Controls are not optional. Any CRA plate run in this lab for any reason must have proper controls on it. No excuses, no exceptions. And these are the only acceptable control strains. Staph epi ATC 35984 is your positive. It must give you a strong black crystalline result. ATC 12228 is your negative. It must be pink and smooth. If your controls don't look exactly like they should, the entire batch of plates is considered invalid. You throw it out and start over, period. Okay, this is your final summary. Think of this as the review for your competency assessment. These are the 5 critical pitfalls of the CRA Fest. 1, it's subjective. 2, it's not standardized. 3, it's too specific and misses important biofilms. 4, it's confounded by pH changes. And 5, its performance on key pathogens is terrible. Know these 5 points inside and out. So I'm going to leave you with this one final question to ask yourself every single day when you're at the bench. Our job is to provide doctors with reliable data that helps them treat patients. So ask yourself, is the test I'm about to run going to provide real, trustworthy data, or is it just going to give me a pretty color? From now on in this lab, we choose data. That's all for this training.